faculty and staff that are here with us today. And then as well as Professor David Levinson, who is here with us from Sydney, Australia. It is currently about 8 a.m. there. So I just want to thank everybody for their attendance. So the title of my work over the last few months is Accessibility Impacts of Bus Access to Managed Lanes. And this title might be a little confusing to some of you who aren't familiar with these terms. So in a bit, I'll go through the definitions of what these words mean, but I'm going to start off by telling you the premise of this work. Okay. So the question can be posed, what can managed lanes do for transit accessibility? And so with managed lanes and general purpose lanes, we're talking about two different highway operating environments. And so when we have different operating environments for buses to use, we're going to have different travel speeds. And so depending on the highway, or depending on what highway facility a bus is using, the bus might experience different travel times along that segment. And when there's a difference in travel time, there might be a difference in the number of opportunities that can be reached within a certain travel time threshold. And that's what we're talking about when we talk about accessibility. But managed lanes do offer potentially a faster and more reliable highway operating environment as opposed to general purpose lanes, which is what we all typically drive in. And so when the conditions are right, passengers on transit vehicles may feel or may have a benefit in terms of their job accessibility due to the managed lane operating environment. And this type of operating environment has not ever been incorporated into accessibility calculations in the past, and so that is what this work is all about. So now for defining some of these terms. The general term accessibility, taken from the Oxford Living English Dictionary, is defined as the quality of being able to be reached or entered. So that's a great introduction to the word, and you might be familiar with it from other contexts such as the ADA compliance, Americans with Disabilities Act, which refers to accessibility like to accessible signals or accessible ramps. But we're not talking about that term. Instead, we're talking about more of the transportation in the transportation context. And so in 2006, a project or work done looking at different accessibility metrics by Ahmed El-Ghanadi and Professor David Levinson, they redefined accessibility in the transportation context as the ease of reaching valued destinations. And so now you can see the intermingling of land use and the transportation network. So land use coming in the form of valued destinations, as that part of the definition, and then the transportation network as the ease of reaching, or the mobility along the transportation network to reach those valued destinations. And so there are many ways to define accessibility, and some of them are very complex, and of course that means more data and more time. The metric that the Accessibility Observatory uses, for which this project is within, we use a location-based cumulative opportunities measure, which is defined as the total number of opportunities that can be reached from a given location within a particular travel time threshold. Okay, so what does that mean? For an example, we're all sitting here in the civil engineering building. And if someone gave us, let's say, 20 minutes to travel in any and all directions, and then to sum up the number of valued destinations, say jobs, that could be reached within that travel time threshold, that value would be what's summed and put on this origin spot. And that travel time includes walking to the bus stop, kept waiting for the bus, riding on the bus, and then egressing or getting off the bus and reaching the destination. And so all of that can be maybe performed simply for a single origin, but if we're doing this for thousands of origins and hundreds of thousands of destinations, then suddenly the problem becomes very complex. So that gets at one part of this research, which was the accessibility portion. But now I want to define managed lanes, which They have many definitions across the country in terms of how managed lanes are applied, but we're familiar with with a few of them, and so I'll talk about them now. The Federal Highway Administration defines managed lanes as highway facilities or a set of lanes where operational strategies are proactively implemented and managed in response to changing conditions. So we're familiar with perhaps HOV lanes, which came about in the 1970s after the oil embargo and the Clean Air Act, which was a good incentive for people and the Federal Highway Administration and other agencies to incentivize high occupancy travel, so transit vehicles or buses and light rail and so on and so forth, or carpools. And so HOV lanes were funded and they were built out. However, not always was the capacity utilized to the best of its ability. And so high occupancy toll lanes are another way of adding a layer of vehicle eligibility to the managed lane definition. Suddenly now single occupancy vehicles can pay to use these managed lanes for a price. And that price is managed, as in the definition, managed in response to changing conditions, changing traffic conditions, that is. And so essentially an equilibrium can be reached on managed lanes. And then finally, express lanes are broadly defined using the access type. So express lanes might encompass HOV and HOT lanes, but express lanes also get at if there are large gate arms or other barriers for access that control how the lanes are used. So you might be familiar with MinPass here. That's our form of managed lanes, and they use a combined pricing and vehicle eligibility requirements along with some aspects of access type for the system to work as a whole. So now that you guys are all familiar with the terms of what I'm talking about, I'll get into more of the research specifics. So the goals for this research were to establish a methodology for updating transit vehicle speeds. Why did we want to do that? Because we're looking at managed lanes which provide a different operating environment and thus perhaps different transit vehicle speeds when transit vehicles use those managed lanes. In order to do that, we had to build a computer program that would systematically update the data that informs transit vehicle schedules, and so that's called GTFS data, and I'll talk a little bit more about that later. Then we wanted to test out this methodology and program on a set of routes, so I'll get into that later, and that'll be really interesting to see the results from, and that's where I'll show our analysis of the outcomes. And so now I'm going to get down more into the nitty-gritty methodology aspects. To start off, the title of the computer program that I'm talking about, it's called the Stop Times Editor. And that's because when we're making changes to transit vehicle speed is made up of two components, distance and time. Within the information that we have for transit vehicles, the GTFS data, there is a file called the stop times file, and that lists only time. And so the first point here about an input file and road segment data, that's needed for the computer program to be able to have a distance input and introduce in distance to calculate speed later on. And so the user of the stop times editor creates an input file, and that's where looking at road segment data and other information to break down routes into where managed lanes are being used is key. And so that's a larger file that needs to be created and looked at route by route. But once that's done, a configuration file is built, and that is to tell the computer program where and when changes can be made. So that's a pretty simple file to make. You can list the segments that you'd like to change, a time window for them to be changed over, and then a target speed to set on for that route. But before making or understanding how to implement a test detector data, which is, many of you are familiar with this, but it would capture the traffic on certain freeway segments of the general purpose traffic. So capturing what everyone is traveling like. But then also automatic vehicle location data, or AVL data, should be looked at, and that is only transit vehicle information. And so that's really essential to confirm where the operating speeds are at and what they can reasonably be placed at. After all of this information is looked at, the output is an edited GTFS bundle. And so that's the final aspect of the stop times editor portion of this accessibility calculation process. And so now I'm going to walk through the methodology, or more of the algorithmic process of what the stop times editor is doing. So bear with me, I will try to introduce things gradually here. So the stop times file looks like this. This is just a snippet. You can see there's a trip ID string, arrival, departure times, and a stop ID. So we'll look at this portion here. Each line represents when a bus has arrived at a particular stop. And so if we pull out this portion right here, this is actually a bus trip that's traveling along a managed lane. And so what you'll see here is that at stop 3391, the bus arrives at 7:21. And after that point, it travels on a freeway portion for about 13 minutes until it reaches its next stop at 7:34. This type of information is what the stop times editor is walking its way through and pulling out stop sequences like this that match with the input file to make changes to. So I'll have you keep in mind this labeling for the next few slides where I'm referring to different points in space and time for what the editor is doing. Okay, so this diagram is a visualization of a bus traveling along some trip, and also what the stop times editor kind of looks like to the, or what the stop time file looks like to the stop times editor. So let's start at the top. We have what the GTFS data would tell us for an estimated speed along the managed lane length. At the top, we have stops shown in red. You recall A, B, E, and F. Those are the points in time that we do have. And so we have points A, B, E, and F, but we don't have information at points C and D. And that's needed because we have to essentially estimate the travel time on just the managed lane portion. Because as we know, before you get on a freeway, you have to go on an on-ramp. There's some amount of time between that last stop and the freeway that is unknown. So we need a good way to approximate the travel, or the speed along, or the travel time on access and egress links. So a good way to approximate that is to provide information between the previous links and use the time estimate, or use the speed estimate and apply it to this access egress portion. And then with the input file information where we have distance, we can now work backwards and find the travel time. And that's repeated on either side. Okay, so here's our case where we're traveling, where the GTFS data is listing about 55 kilometers per hour. But if we go down to this bottom portion, this is where, let's say we make a change to the program, or to the stop times file, and we want to bump up the speed to 65 kilometers per hour on just the managed lane portion. What that's going to do for the stop times file is that now the bus should technically be reaching points D, E, and F a little bit sooner in time. And so that's why you're seeing a dotted information here. And so hopefully that gives you an understanding of what would happen when we have to change speed on a certain link, and then how that cascades through to the remaining stop times per trip. Okay, so one last slide with some math, but it's pretty simple math. We're looking at calculating speed and travel time and working backwards with the information we have. So on the right, you'll see some of the notation, really easy distance, the stop time listed in the GTFS file. And then speed and travel time, and then the remaining segments are listed below. So the first portion that I mentioned, for how we appropriately make changes to the stop times file, the goal is to estimate the change in travel time on the managed lane, okay? But we have to start here. We start at the lead leg speed, and that's because we have the distance. This distance is provided through the input file. This is where the user is inputting that distance. But the stop times file lists stop times. So we have points for point B and A, and again for F and E. But when we do that and subtract it off, we now have distance divided by time, and that is speed. So once we have an estimate of speed on these links, that's when we move down to the second set of equations where we apply that speed, and then the distance on the access and egress links, and work backwards to find an estimate of the travel time. Okay, so that's what we needed to know. In order to estimate the GTFS speed, basic speed, on the managed lane link, we have, like I said, we have the information at points E and B, and now that we have an estimate for the access and egress travel time, this bottom portion, this denominator, becomes the estimate of travel time on the managed lane link. Okay, now we have distance divided by time, we have an estimate of speed, and finally, to find the change in travel time on the managed lane link, we take the difference in our target, this travel time based on what our target speed is by what we found from the GTFS data, and that is the final value. That delta T is that's the main component of what is transmitted through in the stop times for that particular trip. This process is repeated over for every particular stop sequence that it comes upon that matches with what is listed in the input file. Okay, so now that I have described this process, I'm going to list a few reasons why for the first portion of those equations might not apply. So in some cases, we have to use a default access or egress speed. And that default speed is selected by the user based on some of that external data that I talked about. And so in the test scenario, which I'm about to get to, I used the average ADL speed across the managed lane portion of the trip or across the two stops on either end for the bus. And so that's what's being applied here. But the reasons for a default speed to be applied, there are 4 of them. The first one has to do with, so if there's no leader leg stop listed, that is going to happen when a park and ride is most likely the cause. So there's no other stop beyond the park and ride out in the suburbs. And so nothing else would be listed, and then we have to use the default speed. Then if the lead and leg stop are close to the access and egress stop, and there's really not a change in time, what's going to happen is the difference will be 0. When 0 is in the denominator, suddenly we'll have an estimate of infinity as speed. That doesn't make sense, so we apply the default speed. For the third case, this has to do with the creation of the input file to limit the amount of effort of the user in creating this file. So if an alternative set of lead leg stops was recorded for this route, some routes have multiple shapes, and a lot of that can be difficult to record because now you're having to find a lot more distances between stops. What can be reasonably done is if the user were to select the lead leg stops that best represent what's happening on the access and egress links. It's fine to do that because really the only thing that's important is estimating the access egress speed. So however we're doing that to get the best estimate is appropriate. And then the fourth one, finally, if the estimated speed, so if we go through the whole process that I talked about, and we find that the access and egress speed is lower than what we've set as the minimum default speed, then we bump it up to the default speed. And that's because there are some cases where having a small difference in the distance that's inaccurate or the time creates a very sensitive estimation per hour that doesn't really apply to an access or egress speed. So Now for the test scenario that we conducted. This was done, we looked at the Twin Cities region. We looked at October 5th in 2016, which is a Wednesday, so it's a really good day to look at traffic conditions. And then from looking at the morning AM peak hour, so from 7 to 9 AM. And we chose Metro Transit routes 156 and 852. And so you can see what this looks like. So I'll walk you through, route 852 extends from Anoka down through Coon Rapids and then to downtown Minneapolis. You can see with this zoomed in area. The dotted portion lists where the bus travels along local or arterial roads, but then the solid portion is where the bus is on I-94, and that is also where we're considering applicable for making speed changes to. Perhaps this would someday be a managed lane. And so, again, then with Route 156, we start in South Minneapolis at Diamond Lake Road, and then extend up on I-35W into the cities. Again, with that, this is a, I-35W is currently in MinPass, has MinPass installed, and has since 2009, and so that is a difference between I-94. So now I want to show you a breakdown of the speeds that are being applied and what's currently out there. So starting with what the average loop detector speed is. So this is taken as an average over our time frame from 7 to 9 a.m. And this is across all lanes of traffic, so including managed lanes and all the general purpose lanes. So in general, this is what the traffic is experiencing. This is in kilometers per hour. And so we see this dip. And what the stop times editor estimates for our speed is at about the minimum, at about 38 kilometers per hour. And that just reflects that the transit agencies are being conservative when they set their schedules. But it's also reassuring that this is what the GTFS editor, or what the stop times editor estimated as a speed. But then you can see our target speed for this segment and for I-94 is about 104 kilometers per hour. That's about 65 miles per hour for those bus with customary units. Yes, so this gives you a sense of what's happening on I-35W northbound, because that's what we're interested in for this time frame where most of the trips are going from the suburbs and then into the city. So now I'll show you an interesting difference that we found when comparing the detection or the loop detector speed. So this is what all vehicles are experiencing during this time frame. On I-35W, where MinPass is installed, you can see the northbound segment that the detection speed is about 50 kilometers per hour, but the AVL, or just the transit vehicle speed, is at about 55.8 kilometers per hour. And so right away we see, okay, the transit vehicles are actually traveling a little bit faster than the average speed. But then that's especially interesting when you look at I-94, where there's no managed lanes installed. But for that southbound direction, the detection speed, or everyone's speed, is on average quite a bit higher than the transit vehicle speed. So this is one of the reasons why we're doing this project and looking at what managed lanes do for transit vehicles, because we do see, at least based on this test case, that there is a difference. And so our target speed you can see here is 104.6. And then the average schedule deviation for these segments, so how delayed are the buses on average? In general, they are delayed by less than a minute to over 2 minutes, depending on the segment. Okay, so now that we're familiar with all of the initial conditions and the changes that were then made, so remember bumping up to 104.6 kilometers per hour, these are the results. As what happens to the accessibility after these speed changes are made. So this heat map is a plot of the average percent change in job accessibility at the 30-minute travel time threshold. Right away, you can see the most distinct areas where there is positive change is in the suburban areas, and the suburban areas that are closest to the freeway segments that we changed. And so you can see over a 100% or 100% increase at least in South Minneapolis. And then, but you do notice on the outer reaches of Route 852 that there is some slight decrease in the accessibility. And this happens possibly from the fact that now that we've sped up our trips, what I should mention is that on average, Route 852 changed in travel time by about 1.8 minutes. Okay, so when we implemented the speed change along I-94, in general, people taking Route 852 arrive in Minneapolis at about 1.8 minutes sooner than they did before. This is for the same situation here. These census block, or this region for Route 156, this route changed by about 7.5 minutes. And so that's part of the reason why you're seeing especially dark region or bigger percent changes in South Minneapolis is that their rides sped up a lot. And what does that mean at the end of the trip? Well, now they've got more time to walk around and collect jobs for that cumulative opportunities measure. And so hopefully that gives you this is like the beginning portion of looking at what accessibility looks like when we manipulate speeds based on our managed lane conditions. So now I'm going to dive in a little bit closer to a few of the census blocks just to get an idea of what this looks like down at the census block level. This map is a little bit a different heat map than before. This is the absolute change within a 60-minute travel time threshold. So if I pull out 3 blocks, Block A in Coon Rapids, B in downtown Minneapolis, and C in South Minneapolis, you can see there are varying levels of change, with Block C being the most. On the next slide, we're going to pull out the accessibility profile for Block A and C. And we're looking at accessibility as a function of time, because accessibility changes as a function of time. And so with our accessibility calculations, we actually perform the calculation for every minute within our test window. So we actually have 120 accessibility values per origin, and that's what's being averaged and shown in those previous heat maps. But here we're pulling out a single census block and looking at what happens over time. And so for Block A, there really isn't a huge change. There is, if you can just see at the bottom and top of this line around 7:30, that at the 60-minute travel time threshold, we are now the updated 60-minute travel time threshold. We have a slight increase in accessibility and then a slight decrease at the top there, but that's not as easy to see. Let's move to Block C, where in South Minneapolis we saw stronger change. To understand this plot, I'll describe two of the peaks and valleys mean. So you can imagine that if you were to walk right up to the bus stop and catch the bus right when it happened to get there, your wait time would be essentially 0. And now that time that maybe you would have spent waiting can be spent downtown collecting jobs until your travel time threshold is up. So that's a peak. But if you arrive and you just happen to miss the bus, suddenly now you have to wait again for a bus, and that's where you see a big drop. And so for Block C, we can see quite a bit of difference between the accessibility levels before in the baseline in blue, and then with our updated speeds for Route 156 especially, in orange here. And so now I'll pull out another visualization of information, and we're getting close to the end. So for this, we decided that perhaps we can look at the entire metropolitan region, but maybe that's not saying as much as what's really happening around transit stops for these two routes, because studies have shown that the closer you live to a transit stop. So I made 2 regions, the entire metropolitan region And then where you see these buffers, each of those is buffered a half kilometer around a transit stop. And so that is called, I'm referring to those as that's the impact zone. And so breaking that down, there's a lot of information in this table, but what I really want to pull out is the percent change between the different thresholds and then between the different zones. So the percent change at the 30-minute travel time threshold for the entire metropolitan area is 0.26. We see a 0.26% increase in our job accessibility levels. And for this measure is the worker-weighted average accessibility. I should define that because weighting the accessibility, the average accessibility by the number of workers in an origin is probably a more reasonable way to, or a better way to understand the information, because now we can say, okay, well, this block that has more workers and has better job accessibility, that should mean more than a place that has not a lot of workers but really good job accessibility. So that's what this means. So backtracking there, but now going back to the percent change in the worker-weighted average accessibility. You see a small increase across the whole metropolitan region, but moving to that impact area, within a half kilometer of the transit stops, now we're seeing about an 11% increase at the 30-minute travel time threshold. And that is because the change in time that we're experiencing for these trips, like I said, between 1.5 minutes and 7.5 minutes, that's pretty impactful when suddenly you add that to your 30-minute travel time threshold. That most of that means that you can walk around an extra 1.5 to 7.5 minutes to collect more jobs in the destination. And so, of course, 1 to 7 minutes is a bigger proportion out of 30 minutes than it is for 60 minutes. And so that's why you see a smaller increase at 2.03% for the 60-minute travel time threshold. So those are some of the main results from this test scenario. And so now I'm just going to go through some program enhancements that we've thought of along the way, and then I'll wrap up. So like I mentioned earlier, there were some reasons for using a default speed as opposed to relying on the estimation process. And at this point, the default speed was always applied in the test scenario. And so we would like to get away from relying so much on that default speed and instead looking more at, or trying to use, seeing if using just the GTFS estimated speeds across from river points B and E. That's one of the ways that we've been considering for getting around this issue of just applying the default speed. And then another issue that we came across is that some express routes run way out into the exurban areas. And what that does is create a really long access link. And so if we've applied the wrong or slightly inaccurate default speed across that entire length, now that problem is cascading through to for the change or the travel time, the estimated travel time would become far skewed, and now we've got poor estimates for the managed lane travel time. So both of those reasons are why we want to reassess some of the initial portions of the access and egress speed estimation, but I think we've made already some good progress on understanding where we can start making those changes. Some other, and one drawback is that, referring to all these external data sources, that's needed. As a researcher, you should always be looking at other sources of data to understand the problem in a holistic sense. But of course, considering all, getting all AVL data sets for, upwards of 100 different transit routes could be difficult. So if there was a way to eliminate the need or reduce the need for all these extra data sources, that would be beneficial perhaps. And then finally, when we create the input file, that does list distances, and at this point, it's a human being adding up the distances between stops. And of course, when you have human input, that's prone to error. So perhaps using a map matching algorithm, which we've started to consider, would be appropriate and expedite this whole process. So in conclusion, this research, remember, it introduced a methodology and a computer program for incorporating new highway facilities or operating environments into the accessibility calculation process. And for this test scenario, we saw that there was an increase in the impact zones of between 2 and 11%, depending on the travel time threshold for the worker-weighted average accessibility. And while these results are preliminary, they demonstrate the need for incorporating these other types of highway facilities into our accessibility calculations. And so it's exciting to see some of these results because we already have a much larger scale version of this in the works with an entire look at the managed lane system in Minnesota, or in the Twin Cities. And so we've been working on that already, and it's been great. So with that, I would like to acknowledge a few people, and then I'll take questions. So